Everyone wants gas. It's clean, efficient, and with large reserves available, gas will play an increasingly vital role in satisfying the UK's energy needs for a long time to come. In order to meet future consumer demand, National Grid Transco has made a commitment to increase its gas transmission capacity from the St Fergus terminal near Peterhead. The second phase of this project required the laying of a 50-kilometre, 48-inch pipeline from Aberdeen to Lochside near Montrose. To do so quickly and safely without damaging the area's wildlife or agricultural productivity presented a huge challenge.
If National Grid Transco are to deliver this project in a challenging 6-month period, we've got to stay flexible, we've got to anticipate problems and communicate with our stakeholders.
Phase 2 of NGT's Feeder 24 pipeline began life in January 2002 with the creation of a simple 5-page document. Physically putting the pipeline in the ground was only half the challenge. An enormous amount of preparation, planning and management was required before an ounce of topsoil could be stripped, and this detailed management had to continue throughout the project. In August 2002, the project team began examining the pipeline route development, its detailed design, land acquisition issues, and numerous environmental surveys and consultations. By June 2003, the conceptual design was complete. Shortly afterwards, the environmental statement was finalised for submission to the Scottish Executive. This enabled the final detailed design to be ready by November 2003.
The biggest hurdle within the planning stage of this pipeline is getting permission from the Scottish Executive to build the pipeline route that we wanted, bearing in mind it's a 48-inch diameter pipeline going through a very congested corridor, using international contractors and suppliers within the timescales that we were given to do so.
After lengthy discussions and consultations with the Scottish Executive, consent for site construction was finally granted on the 30th of March 2004. NGT set to work that very day with a commissioning target of November 2004. The clock was ticking. Only contractors who meet stringent quality, safety and environmental criteria are allowed to work on National Grid Transco projects. The design and build contract for this pipeline was awarded to Entrepose. An important part of the planning process involved close liaison with local farmers in an effort to reduce the impact of the pipeline on the agricultural community. Farmers were mainly concerned with the condition of their land after reinstatement and its quick return to full production. NGT had to pay special attention to avoid spreading soil-borne diseases such as potato cyst and eelworm. The protection of private water supplies and the location of access crossing points also needed careful thought. A 43-metre wide working corridor known as the right-of-way had been agreed with farming organisations and landowners. Accurately fencing off its entire length established the boundaries of the pipeline's route and kept the working area secure from animals and the general public. During the pipeline's construction, many small rivers and streams had to be crossed by vehicles and heavy plant. Small bridges or flume pipes were carefully laid to allow access along the right-of-way, while at the same time protecting the riverbanks and wildlife. Topsoil then had to be stripped from the right-of-way to prevent plant and machinery damaging the organic soil structure. Excavators pulled back the soil, carefully stripping to a depth consistent with the varying thickness of topsoil. This soil was then pushed back to the fence line, leaving the surface at subsoil level, ready for heavy construction work to begin. During this process, NGT stipulated that an archaeologist be present to observe the subsoil being exposed and to investigate any potential areas of archaeological interest. There turned out to be plenty. All archaeological work followed the Institute of Field Archaeologists' Code of Conduct, as well as national policy planning guidance. As part of this process, the planning team consulted with the County Council archaeologist early in the project and maintained this liaison throughout topsoil stripping. By working closely with the expert archaeologists, NGT ensured that these sites were extensively investigated with only minimal disruption to construction.
Only as a result of Transco laying this pipeline have we had this unique opportunity to work on a number of prehistoric sites in rural Aberdeenshire. We've had several examples of prehistoric roundhouses. We also have part of a prehistoric Iron Age settlement, and there was a very well-preserved example of a grinding stone found. It's just been a fabulous opportunity.
By May, work was already underway stringing the pipeline along the 50-kilometre route. All 3,073 pipes were manufactured by Europipe in Germany to NGT specification. Produced in 12-metre and 18-metre lengths and 1.2 metres in diameter, these X80 grade steel pipes are the largest and highest strength pipes used in the UK gas industry. Prior to transporting the pipes to the site, a traffic management plan was agreed with local councils and the police. This covered route and load issues as well as safety concerns about pipe transporters crossing the busy A90 dual carriageway. Due to Aberdeenshire's undulating countryside, bends had to be introduced into individual pipes. These were either hot bends, specially manufactured in the factory, or cold bends, made from the straight-line pipe. Cold bending was used where possible, as it proved more economical and more conducive to the mainline welding process. Straight pipes were inserted into the bending machine by a side boom. An internal mandrel was placed at the location of the bend to prevent pipe deformation. Powerful hydraulic rams then pushed the cold steel pipe vertically against an anvil in a series of small bend increments, typically half a degree every 400 millimetres. The pipeline route encountered many natural and man-made obstacles. 7 rivers, 27 roads and an intercity railway line had to be crossed using a range of non-open-cut or trenchless techniques. The varied ground conditions needed bespoke solutions, and the trenchless crossings employed a range of microtunnelling, pipe jacking and auger boring techniques. Attention to drainage plays a vital role in land management. All existing drains along the route were identified and their condition and location recorded. Pre-construction drainage was installed after topsoil removal to intercept and preserve those drainage schemes which risked being damaged during construction of the pipeline. National Grid Transco takes pride in its protection of the environment and aims to reinstate land as close to, if not better than, its pre-construction condition. In order to achieve this, a systematic route selection process ranks environmental issues alongside safety and engineering factors. This detailed planning ensures that NGT fulfills not only its legal requirements, but also its moral obligation to protect the environment. Silty water can have very damaging effects on watercourses. SEPA, the Scottish Environment Protection Agency, strictly polices pipeline activities and the risk of silt pollution. Due to the summer's unusually high rainfall, NGT faced a major challenge to control the large volume of water running off the steep slopes of the working width. The solution was to pump the water into specially prepared lagoons to allow the silt to settle.
Companies like Transco have a really high-profile safety culture, but I'm really pleased to see that the environment culture is taking it as high a priority.
The River Dee was the largest watercourse to be crossed by the pipeline. A designated candidate special area of conservation, it is home to protected species such as salmon, freshwater pearl mussels and otters. As a result, stringent environmental constraints were imposed on working hours, working methods, vibration levels and water pollution. The risk of drilling lubricant breakout also had to be strictly controlled, and work or floodlighting at night was prohibited to avoid disrupting nocturnal salmon migration. It was decided that the crossing would be constructed using a microtunnel. In order to avoid deep, open-cut excavations, the tunnel had to be driven under the north bank until it reached a cover of only 2 metres. This required a tunnel 230 metres long and 1.9 metres in diameter. A segmental shaft 7.5 metres in diameter and 22 metres deep then had to be constructed on the south bank in order to launch the TBM, a major engineering exercise in its own right. As the topsoil stripping and pipe stringing worked their way north, contractors began welding sections of the mainline pipe. First, the pipes had to be bevelled. A hydraulically powered rotary pipe-facing machine cut the end of the pipe to the required profile. Constant checks were made to ensure that the bevel profile was within the strict tolerances needed to avoid weld defects. National Grid Transco encourages the use of automatic welding for large diameter gas pipelines in the UK. This project used a fully automated process in order to produce high-speed, high-quality welds. By employing an internal clamp with a copper backing strip, all welding was able to be done from the outside. The integrity of the weld then had to be tested. NGT specified the use of automatic ultrasonic inspection, as this system is safer, cleaner and quicker than radiography, providing acceptance or rejection of a weld almost immediately. Once a weld had been accepted, it was then coated with a fusion-bonded epoxy resin. Health and safety is the #1 priority on all NGT projects, and a pipeline of this scale inevitably raised important health and safety issues. Deep excavations, heavy plant and machinery, large pipes and pipe strings, overhead power lines, and the fire risk from welding operations all contributed to an increased potential for danger on site. To combat this, a project health and safety plan was compiled prior to the start of the construction phase. This document identified the statutory responsibilities of the client and contractor, and outlined the control measures to be adopted to ensure that all staff employed in the project were adequately trained and qualified.
Transco are trying to get the influence from the workforce and get them to believe in their own safety. And if we can get the culture coming from the bottom upwards rather than from the management downwards, we should end up with a better project and a lot safer project.
The centre line of the 50-kilometre route had been set out using highly accurate GPS technology. This route covered ground which varied from sands to gravels to areas of rock which had to be blasted to enable excavation. Working with explosives always creates safety issues. Particular care had to be taken to protect employees, other buried pipelines and any overhead cables located near the blasting. As a result, all the works were rigorously supervised under a permit-to-work system. Crawler rigs first drilled a series of 110mm holes up to 3 metres deep at 1 metre centres, staggered across the width of the trench. Explosive charges were then placed in the holes.
Fire!
A tiny delay between each detonation created an explosive ripple that maximised the blasting effect while minimising the impact on the surrounding area. Work was now well underway excavating the trench. Excavators positioned astride the centre line dug to a minimum depth of 2.4 metres across fields, giving a minimum depth of cover to the pipe of 1.2 metres. Such deep trenches face an increased risk of collapsing, and it was important that the sides were battered to give a wider profile at the top. Working with a banksman, the trenching teams excavated an average of 600 metres a day. As the route was being excavated, welded sections of pipe were being lowered into the trench. Ditching heavy pipe strings in lengths of up to 1,000 metres is a critical operation, requiring skilled operators and excellent teamwork. The use of roller belts helped accelerate the process, enabling the teams to safely ditch up to 1 kilometre of pipeline a day. Crossing the River Carron presented particular challenges. Although a small river, it was situated in a deep, narrow ravine with a railway to the north. The surrounding woodland was designated as a site of special scientific interest. Detailed planning concluded that an open-cut crossing technique would be quicker than an auger bore and have less associated risk. This plan was discussed and developed with all the environmental consultees before being given the go-ahead. A temporary diversion channel was constructed to allow the river to bypass the crossing area. Electro-fishing had already safely moved the fish population away from the works area, and nets prevented their premature return. The river was then blocked and the flow diverted through the temporary channel, rejoining the river downstream. Lining the temporary channel minimised silt pollution. The trench was then dug in the dry main channel. The pipe section to cross the river had been prefabricated into a contoured shape, allowing it to be quickly lowered into place. After backfilling, the riverbed was thoroughly reinstated, the main channel unblocked and the river allowed to flow back through its natural route. Taking only 2 days and creating minimal disruption to the environment, the crossing of the River Carron was a great success. Preparation of the shaft on the River Dee crossing was now complete, and the process of tunnelling beneath the 60-metre river began. Guided by a laser, the boring machine was pushed forward by a large hydraulic jacking frame. On reaching its limit, the rams were withdrawn, the power, control and lubricant cables and pipes disconnected, and the next concrete jacking pipe lowered into the gap. The cables and pipes were then reconnected and tunnelling started all over again. However, the pipe crossing was located in an area of mixed ground conditions. Sands, gravels and large granite boulders made tunnelling very difficult, as the mixed conditions forced compromises on the choice of drill head. In addition, the water table was very high. To prevent breakout of the drilling lubricant, the microtunnel had to be a minimum depth of 7 metres below the riverbed. A gel compound was also added to the lubricant to stop it migrating through the sands and gravels. During this process, the tunnelling machine pumped excavated material back via the pipes to a screening plant, where all solids were removed and the bentonite lubricant reused. By August, work on the pipeline was in full swing. From the topsoil and trenching teams working at the northern end down to the reinstatement work beginning to the south, the whole pipeline process was moving forward rapidly. Teamwork played an important role. Numerous subcontractors carried out various specialist operations, and with up to 500 personnel from around the world working on the project, strong partnerships and effective communication were vital. On this pipeline, NGT decided to use a semi-automatic tie-in technique, a hybrid welding procedure combining manual and automatic systems. This had been developed for both tie-in and fabrication situations where it was impractical to use the mainline welding crew. When hybrid welding, the first 3 passes